Okay, welcome everyone. This is the week 7 webinar. So we're now on the, we're past the median or the mean because it's actually symmetric. Kind of symmetric, I guess. Maybe not because we had holidays, before, but we're past. And I figured I'd tell you about the plan today. And I want to mention again, I apologize that at the last minute I had to change the time. But jury duty is one thing that when they call you, you don't really have any choice. So I had to go. But the good news is I got there, waited for an hour or so, and the judge says, case has been dealt with, you're all dismissed. So it's over. So the good news is I'm done with jury duty for at least a year. So that's a good thing. And in fact, I'll even talk about some jury stuff that I've had experience, and maybe you have also, but when we talk about what we're talking today. So as usual, I'm going to start out with always any questions that you have. And throughout the webinar, if you have any questions, just, chime on in. I'll be watching the chat box. You can also talk if you want. And the whole routine with the YouTube thing. So chat box is not on, talking is. So then we're going to get into hypothesis testing. And I want to make sure that you understand not to take this lightly, because that's all we're going to be doing pretty much for the rest of this class. So today is the day to learn what it's all about. And for pretty much for every single week for the rest of this entire course, we're going to be doing hypothesis testing. Okay, there's going to be some other things we'll do while we're doing hypothesis testing, but mostly that's all we're going to do. And the funny thing is you've all done it before, not with heavy statistics. And you may not remember it because you probably did it in 7th or 8th grade. And it's called the scientific method. It's required of every middle school kid, but it doesn't mean you remember it because some of you, it's been a long time, but you've heard of the scientific method and that's what we're doing. So what we're going to do, I'll go through the process of hypothesis testing. And I want to mention, I've listed what we're doing today in order, but it's more than just a lecture in order. This is the order at which you do hypothesis testing. Okay, you even start with Q&A. Start ideas. Let's ask some questions and see if we have any answers. Just thoughts. That's all this is. Then the next thing you do in hypothesis testing is the null and alternative hypotheses. Those are basically your idea. What you're trying to show is true versus what the other guy's saying, nah, it's not true. So I'll go into all the details, but I want to talk about, then we'll talk about the type 1 and type 2 errors. You might have heard of them in different language before. And in the medical field, they often call those false positives and false negatives. Have you heard of that before? Probably. If you haven't, that's okay. But type 1 and type 2 errors is that's our main thing today. Okay, so then based on the type 1 and type 2 error, we're going to decide on the level of significance, which is kind of really similar to the confidence level. Remember, you had a 95% confidence, except it's backwards. Okay, and don't shoot the messenger. I'm not the one that did this, but everyone in the world does it. You want to be 95% confident that you're right. And it turns out when you're doing hypothesis test, you want to be only 5% chance of being wrong. So unfortunately, that's just the way it is. Sorry, don't get mad at me for this one. It's like, what were they thinking? So that's what we do. Then we'll get into the p-value. And we've done the p-value, but in a sneaky way, as in I snuck it in, not in week 6, but in week 5, basically, I made you find the p-value for your discussion post reply. Remember, you had to find a probability of something using a normal distribution. So that, it turns out, is the p-value. We just didn't call it the p-value. But now we're going to have something called the p-value. We're going to take that p-value and the level of significance, and in the combination of those two things, we're going to decide whether or not our idea was right. And if our idea is right, we're going to say, yes, we got it. We're right. And if we decide that we don't have evidence to show our idea is right, we don't say, no, we're wrong. We just say, I don't really know anymore. So in this chapter, and pretty much for the rest of the course, never admit you're wrong. Got it? Only admit you're right. And that's going to be a biggie for this class. Okay, and then we'll interpret the p-value. And this is going to get into kind of like interpreting the confidence level, where it was a lot of words. Do you remember that? Same thing with interpreting the p-value. And then we're also going to interpret the level of significance, also a lot of words. So get ready. Get ready for that. So this is a very, very verbose chapter. So be ready for it. Then at the very end, we're not quite completely ready yet, but we can just chat about it a bit, and that's Project 2 planning. Next week is really when you'll be ready for really focusing on Project 2. And Project 2 is not due until the end of week 11, and we're in week 7. So, you got more than 4 weeks. You got plenty of time. But next week, I won't say that anymore. Next week, you need to really work on it. This week, you should just be thinking a little bit about it. That's all. So that is the plan for the webinar. And hopefully you'll all catch on a bit. I do want to let you know that this stuff is very deep. Some of it you won't fully understand. But as I mentioned at the beginning, we're going to spend the entire rest of this course on this. So you're going to have week after week more practice. So today is the introduction on this hard stuff, but we'll keep learning it. Does that make sense? So, but you can still ask questions. And I'm going to give you another piece, and that is, we're not going to do the heavy mathematics of this because it's too hard. So as you might guess, I created calculators for this stuff. And I'm going to mention one more thing before I get into the details. And that is that it has some of the same main concepts as confidence intervals. Do you remember the first step when you do a confidence interval? What was the first step? The first thing you think about? I mentioned it. It's been a week that I told you, but. And remember? You think about the survey question and say, is the answer to the survey question going to be yes or no? Or is the answer going to be a number? Do you remember that? So that very important piece for confidence intervals is just as important for hypothesis testing. So if you can't come up with the survey question, decide and force yourself to decide, is it a yes, no, or is it a number answer? It'll be a disaster for you. Okay. And hopefully you got practice last week on it. I did notice, I want to let you know I've graded everything. So I finished grading this morning. I did notice that some of you in your write-up on the last couple questions, use the word mean when it wasn't supposed to be mean, and use the word proportion when it wasn't supposed to be proportion. And that means you don't have that down on, is it yes, no, or is it a quantitative? Get that down. It doesn't go away. So you have to get that down. Does that make sense? So that is important. Okay. If you can't do that, this whole thing is going to fall apart. Any questions about anything as we go? Any questions? Okay, if there's no questions, let's talk about the null and alternative hypothesis. And I'm going to have lots of examples. And the great thing is it's really easy to find real world examples. I'll even use the example that came up or could have come up this morning for me. What was that? You should all know what I was dealing with this morning. You remember? Jury duty. And when you're a jury, okay, now it turned out that the case was dismissed, but had the case not been dismissed, had I actually sat on the jury, and I've been a juror before, okay? It's not by choice, by the way. They choose me. I don't choose to be one, but I've been a juror. At the very end, you have to make a decision. You have to make a decision on what? The big decision. What is the big decision the jury has to make? Hopefully you all know. You can put the chat box if you want or whatever.
If someone's guilty or not guilty.
Yeah, someone's guilty or if someone's not guilty. Okay. And the way it works in terms of jury duty, being a juror, which works really well for explaining everything we're doing today, actually, is they sit there, the lawyers, right? And they give you the evidence. And you've probably heard they have to give you enough evidence that you feel they're guilty beyond a shadow of a doubt. Does that make sense? You've heard of that probably, right, before? Those words? All right. Well, in statistics, the shadow of the doubt is typically less than 5%. And that's your shadow. Okay. So it's never 100%, but less than 5%. And if you don't have that less than 5%, if there's a 40% chance they're innocent, you're not gonna say that they're guilty, right? Even though there's a higher chance of being guilty, but it's not enough. Any questions on that idea? So in the guilty or innocent thing, the null hypothesis is that they're innocent. And that's kind of the status quo. You're always trying to show the null hypothesis is false, and you're trying to show that the alternative hypothesis is true. Okay. By the way, the defense attorney does not try to show they're innocent. The defense attorney is trying to show there isn't enough evidence to show they're guilty. Do you see the difference? In fact, when I was on a jury, when I actually had to be there for a week, I still thought there's a very good chance the person was guilty, but not a good enough chance. And there wasn't enough evidence to really put the person in jail. Do you see how that works? So the null hypothesis is that status quo idea. The alternative hypothesis is what you're trying to show is correct, is true. You're trying to show something that's like maybe people haven't noticed before, or maybe a main thing that is true. You're trying to change somebody's mind usually. Okay, let me give you the example, the most important example, and my guess is you'll agree, that's happened in the last 3 years, and that is COVID vaccination. Okay, and hopefully you understand, I'm a statistics professor. I looked at every detail before I got vaccinated to make sure that they did it right. Does that make sense? Okay, so let me show you how it worked. And this is real, by the way. Okay, at the time when they were testing to see if the vaccination works or not. Okay, and when I say they, there was more than one test, and you may or may not know the reason or the history, because there was Pfizer doing the test. Do you remember that? There was Moderna doing the test. There's also J&J doing the test, right? And they're all testing different things, but they all had to test. They all had to show that their vaccine worked. Well, what does it mean for the vaccine to work? Okay, and I'm going to do one piece of it. There's a few pieces. One of the main pieces is that those who are vaccinated have a smaller probability of getting COVID. If you get vaccinated and you have a smaller probability of getting COVID, then the vaccine works. That doesn't mean you have a 0 probability of getting COVID, but a smaller probability. Any questions on that? And at the time when they were testing to see if the vaccinations were working, there was a 4% probability that someone would get COVID over the trial period. So that what they do is they give you the vaccination and then they watch you for some months and then they see if you got COVID at the end of that. Does that make sense? That's how they did it. Okay. And so what we're looking at is the probability that we want to see, are you less than 4%? So H naught is, no, you're not. The vaccination is useless. And you still have a 4% chance. You just you had to take the stupid shot and it didn't help at all. Do you see that? So first thing, H, I want to mention these things. It's very important. Letter H stands for, any guess? It's the first letter of an important word in this chapter. It's the important word, right? Hypothesis. Okay, I didn't see it in the chat box, but the letter H stands for the hypothesis. And I want to let you know the British got to this before the Americans did. Do you know how the British say this number here? Okay, they don't say 0, by the way. That's what we say, right? The British say not. So the British got to it before, and again, don't get mad at me. You can get mad at the British if you want, but everyone calls it H naught. And that is same thing as H0. Okay. And then I want to let you know, this is important. This little thing right here is not an equal sign. Hopefully you can see that. Can you all see that's not an equal sign right there? What is that? It's on the keyboard.
Colon.
Yeah, it's a colon. Okay. There's a reason why I'm spending time saying this. Okay, because so many students screw up and they write H naught equals. Don't do that. It's always, for everything we do in this entire rest of the course, basically, it's going to be H sub 0, which is called in British H naught, colon. And then, this is very important, you have to decide what the survey question was. What is a survey question for the COVID test?
If it works or not.
Yeah, what does it mean to work?
To not get sick.
Yeah, so the survey question is, did you get COVID?
Oh.
Right? And if you ask me, did you get COVID? Have you had COVID this year, this calendar year? What am I going to say? Unfortunately, yes. It sucked, but fortunately, I'm better now. Come to my office, by the way, office hours, I'm totally safe, by the way. It's been a couple months, but I did get COVID. So it's a yes, no question. Got it? When you have a yes, no question, we use the letter P because P stands for proportion. If it wasn't a yes, no question, instead of did you get COVID, if it was something like, I don't know, what was your temperature? Then you wouldn't use the letter P, you'd use the letter mu. So it's very important to know whether you're using P or mu. And it will take off points if you get that wrong. I took off points on your exam, by the way, if you wrote mean instead of proportion or proportion instead of mean, and I warned you in the webinars past, I'm warning you again. It's very important. Got it? And then always in H naught, in this class, by the way, just let you know, it'll be equal sign after that. Okay, there's some books that don't use that. Most books will use equal sign. I like equal there's all kinds of reasons for equal, and it's just better. Okay, and then in this case, it's P equals 0.04 because at the time that they were doing the vaccination trials, 4% of the population was getting COVID in that time. So if the vaccination didn't work, that means you have a 4% chance of getting COVID, right? If the vaccination works, and let's talk about that next. So now we're going to write H1. I want to give you a heads up. Not all books will use 1. Some will use A. It's a little confusing. I tend to use 1 because 0 and 1 tend to match pretty well. But some use A, and they use A for the word alternative. Okay, and if you write it with an A, I'm okay with that. Okay, if you write with a Q, I'm not okay, by the way. This guy for the null hypothesis is always not. It's always a 0. Okay, and then always colon. And always, everything is exactly the same. See the P? We had a P before, but now we have less than, because what was Moderna trying to show?
The least amount of people that would get sick.
Yeah, not the least amount of people, but a fewer proportion of people get sick.
Okay.
Right? Least is a word that's comparative, kind of it's fewer. Fewer get sick when they get vaccinated than if they hadn't gotten vaccinated. And if fewer get sick when they get vaccinated, then you should vaccinate people. Do you see that? Whereas if fewer don't get sick when you get vaccinated, what's the point? Okay, there was a second thing with death and hospitalizations, but again, I don't want to get too complicated. But so we're just going for the sickness. Sound good? Okay, so P is less than 0.04. This number 0.04 here and this number here will always match. Those have to be the same number. Got it? Okay, so that's important. Okay, this first piece is called the mole hypothesis, and the second is called the alternative hypothesis. Again, sometimes you don't do proportions, sometimes you could do means. Okay, so again, you might want to say, I mean, there's all kinds of tests for means. You might want to say, does advertisement help my revenue if I'm a business person? And if it helps the revenue, then you would have a mu equals whatever your revenue is without advertisement. Do you see? And then mu would be greater than whatever the revenue would be without advertisement. Because if it helps, that means you get more revenue. Do you see? But you use mu instead of P because the survey question would be, what was your revenue after you advertised? Do you see? And the answer would be $20,000 or whatever it might be. Does that make sense? So be ready for that. And by the way, we're going to have more things too next week, but this week we're just going to have P and mu. Any questions so far? Okay, so now comes what's going to be called the type 1 and type 2 errors. Okay, so when you do a hypothesis test, and you can imagine this vaccination idea, is what they did, and if you don't know, then I'll tell you, they actually grabbed 40,000 people to be test subjects. Okay, by the way, is 40,000 a lot? Okay, sounds like a lot. I mean, if I made you do 40,000 people for your project, you would like quit my class, right? So it's a lot of work to do 40,000 people. To find 40,000 volunteers to get tested for a vaccination that they don't know if it even works or maybe kills you or whatever. Do you see? You got to get volunteers. Okay. By the way, I know this firsthand from the other side. I've been a volunteer, not for COVID, but for diarrhea to medicine. This was there was an advertisement: if you have the runs, run to our medical clinic. This was when I was at UC San Diego, and I was having a bad day, if you know what I mean. And they gave me $100, and I turned out to be the placebo person, and I didn't feel better. It was awful. But I remember it. So I was one of them. Okay, so what could happen is, what if they said by that 40,000 people, what if they just had luck and a bunch of those 40,000 people, most of them didn't get COVID? A lot fewer got COVID than you would expect. What's going to happen? They're going to say, yeah, it works because fewer people are getting COVID from our test of 40,000 people. And guess what? The vaccination doesn't work. Okay. So the other thing that could happen is the opposite. Maybe the vaccination does work, but there were just like a bunch of people that got really bad luck and they still got COVID. And they weren't able to say that the vaccination works. Those are the kind of errors. So let me give you the definitions. So type 1 error is rejecting the null hypothesis when the null hypothesis is true. And I want to let you know, if you reject the null hypothesis, that means that you are saying that this is wrong. P is 0.4 is wrong, which means that your idea, P is less than 0.4, is right. That's what it means to reject. If you reject the null hypothesis, you accept the alternative hypothesis. Those go together. But the null hypothesis is actually true. So I want to write down a word that a lot of people don't know. This is not a math word, by the way. This is an English word. And it's ramifications. Have you heard of that word? Ramifications. So ramifications, I want to let you know, is kind of, I want to give you the easy way of saying that word. The bad stuff that happens if this stuff happens. Does that make sense? But the one word way of saying it is the ramifications. Okay. And if you have a type 1 error, by the way, there's going to be bad stuff that happens. Okay. It turns out we'll have a type 2, and that's still bad stuff that happens. So think about it. If we reject the null hypothesis, that means we're going to accept that P is really less than 0.4. And if we accept, and we meaning the health agencies, right? World Health Organization, that kind of group. And they're going to accept that the vaccination works. But the null hypothesis is true, which means the vaccination doesn't work. So what does that mean? They're going to approve the vaccine gets approved. So the vaccine gets approved, but it doesn't work. That's not a good thing, is it? All kinds of bad things happen. One is people have to go through the vaccination process. Hopefully you got vaccinated, by the way. Was that a fun thing, like the day after you got vaccinated? No, I mean, for me, I was so tired. Okay, I was so tired the day after. And then if the vaccination doesn't even work, you went through that for no reason. Do you see? Okay, it sucks. And maybe even worse is that after I got vaccinated, okay, what I did is I went and saw my family. I went down to Southern California and I went to see all my family who I hadn't seen in over a year. But had the vaccination not worked, I might have had COVID. Right? And all of a sudden, I'm putting my family in danger. So I'd have been overconfident, and maybe I'd go to some parties and they get COVID, and more people can get COVID. Do you see that? So a type 1 error has some pretty bad ramifications. Do you see that? So those are the ramifications. You don't want it to happen. Here's a type 2 error. Type 2 error is that there's not enough evidence to reject the null hypothesis. We say we failed to reject when the null hypothesis was false. So in that case, if we don't have enough evidence to reject this, that means we're not able to say that P is less than 0.04. And what's the World Health Organization going to do? They're going to say, nobody should get that vaccination because it doesn't work. But it really does work. And what would happen is the vaccination does not get approved, okay, by the World Health Organization, by the FDA, whichever you're looking at for organizations. It doesn't get approved, but it really works. So nobody gets vaccinated. And 1 million more people still die of COVID because no one got vaccinated. And that'd be awful. Do you agree? They're both awful. Do you agree with that? I want to mention with my jury idea, if you look at the type 1 error, that means you're able to reject the null hypothesis, say that the alternative hypothesis is true, which means that the person, we're going to say the person was guilty. Guilty, 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 right? And what's going to happen to that person? They're going to go to jail. Okay, at least on the one I was in. It was a big meth thing. But the person wasn't guilty. The person wasn't a drug dealer. But we put the person in jail. Is that okay? That's awful. Do you agree? Okay, now a type 2 error is we don't have enough evidence to say the person was guilty. But the person really was a meth dealer. And guess what? The person doesn't go to jail, right? Because the jury wasn't able to find the person guilty. And then the person maybe continues selling meth. That's pretty bad too. Do you see that? Which is worse? And everyone might have a different feeling on which is worse, but in our society, the type 1 error turns out to be worse, is because in our society, that's the beyond a reasonable doubt idea. You don't want to put an innocent person in jail. That's actually worse in our society than not putting them in jail when they're guilty. Okay, so that's, if you don't agree, sorry, but that's our, that's our legal system. That's how it works. Any question on the type 1 and type 2 error for either of those examples? Okay, so again, we're going step by step. First step was to state the null alternative hypotheses. That's the status quo and your idea. Second step is to decide on the type 1 and type 2 error. The third step is to decide on the level of significance. And what we're going to be doing, and I'm going to explain a little bit more later, is the level of significance is the probability of a type 1 error. You want that to be low, right? But it turns out, and the math is too hard for me to show you, that if you make the probability of a type 1 error low, then the probability of a type 2 error gets higher. And vice versa. If you make the probability of a type 1 error high, the probability of a type 2 error gets lower. Okay, in our class, we're going to let 5% be the status quo for the type 2, for the level of significance, which is the probability of a type 1 error. So if a type 1 error is worse, then we want that probability to get smaller. Do you see that? And instead of 5%, we're going to go to 1%. If a type 2 error is worse, then we want the type 1 error to get bigger to make the type 2 error smaller. So we'll go to 10%. So let me explain a little bit. So we have to decide what's worse. For the vaccination, what do you think is worse? Okay. It turns out the type 2 error is probably worse because with COVID time, if we don't have a vaccination, that means you got to live with COVID forever. Aren't you glad that we're done? I mean, we're not completely done, but we actually can, go to the store without a mask and we can actually see friends. Do you see that? Whereas before the vaccination, we really couldn't do any of that. Do you remember how terrible it was? So in a way, a type 2 error would be worse. So if a type 2 error is worse, then we're going to use 0.1. And I want to let you know this letter. Anyone know what that letter is? It's the first letter of the Greek alphabet. And it's alpha. Okay, so it's alpha. And if you don't know how to type it when you're like doing the exam or something, just type ALPHA is how you spell alpha. Okay, but if you know how to use Greek letter stuff, then you can go click on it. On your projects, you need to actually do it because you can get help. Okay, on the exam, you're not supposed to be getting help. Okay, so just note, that's just a note. It's the alpha, it's the first letter of the Greek alphabet. Don't get mad at me for any of these kind of things because I don't choose those letters. But that's what the world chooses. Any questions on that? So we're going to choose a 10% level of significance, or a 0.1 for level of significance. I do want to let you know that this is not like the same as confidence level. Okay. A probability of a type 1 error really has nothing to do with the confidence level. So when you're writing up your project or writing it about anything that you're doing on an exam, do not write, because I chose a 95% confidence level, I'm going to choose a 5% level of significance. You shouldn't do that, because they're separate. You can have a 95% level of confidence and a 10% level of significance, for example. That's allowed. So don't just use one for the other. Got it? Okay, so again, I say a lot of things, and if you do that, I take off points. So hopefully, I mean, I know you are all, the ones that are here right now, are watching this webinar. Some people I know, don't pay attention, and it doesn't go well for them, because I let you know where I take off points, and that's one of the common point taker outers. The next step is the hardest step of the whole thing, but not for you, because usually I'm just going to give you this, and that is collect the data. Because in the real world, all this stuff that we've already done, that might take an hour or two to figure out. Imagine collecting the data when we're talking about the vaccination. You have to vaccinate 40,000 people. Do you know how hard that is? How much work that is? How expensive it is? How hard it is to find those people? So collecting the data in the real world is absolutely the hardest part. Any questions on that? You will not feel that in this class, though, because usually I'll just give you the data, or I'll tell you what the statistics are or whatever. Okay, but any questions on the collect the data? So in project 1, you got to understand the process of collecting the data. That was what project 1 was really a big part of project 1, was how do you collect data? Okay, and I kind of put this in the kind of the same step, but really it's the next step after that is you put the data into the computer. Okay, and by the way, everybody uses a computer. No one does it by hand anymore in the real world. Use a computer. They don't always use my spreadsheet or my computer stuff. There's others out there too, but you put it in the computer and you calculate the p-value. Okay, in a little bit, the p-value is the probability that if the null hypothesis is true, and you did this study with this sample size, that you're going to get something at least this extreme. That's the p-value. We're going to spend a lot more time talking about it. So if you didn't understand what I just said, well, we're going back to it, I promise. Over and over and over again. Okay, for weeks. Okay, then the next thing you do, okay, and all this has to be done in order, by the way, is you compare the p-value with the level of significance. The p-value will be this probability. Now, you had to calculate the p-value, as I mentioned, for your discussion post reply a week and a half ago or so. Okay, the week 5 discussion post reply, you actually had to, I made you compute a p-value, but you didn't know that's what you were doing. But that's what you're doing. Now, we'll be doing it even an easier computer way, but I wanted you to kind of see it using the central limit theorem. If you remember, when we did central limit theorem, I had you compute a p-value without you noticing. Okay. Then what you do is you say, is the p-value small enough? Because if the probability of getting what you got is so small, then given H naught is true, then you get to say, sorry, H naught's not true. I was right. Do you see that? That's how a hypothesis test goes. Whereas if the p-value is not small, and this alpha is that borderline of being small or not small, then you're going to say, we're going to fail to reject the null hypothesis. We're not going to say that H naught was true. You never say that, by the way. We're going to say we don't have enough evidence to say H naught is false. Just like you don't have enough evidence to say the person was guilty. You do not say the person is innocent. You say that we didn't have evidence to show the person's guilty, is how it works. Okay. And same thing with, like the vaccination. You don't really say the vaccination didn't work. You say you didn't have enough evidence to show it worked. Sometimes it means you need a bigger sample size. Sometimes you're just wrong. It didn't work. But you don't know whether you were wrong and it didn't work, or you just had a too small sample size, so you weren't able to show it. Right? Any questions on that idea? Okay, just like if I flip a coin 3 times and I get 2 heads, and I win if I get heads, are you going to say I was cheating? If 2 out of 3 times were heads, are you going to say, well, that's just rare, he obviously cheating? What do you think? If I get 2 heads out of 3 flips, that's normal to get 2 heads out of 3 flips, right? Okay, that could happen. Okay, I mean, you could still say I'm cheating, but you probably, you're not going to say I know the person's cheating. But if I flip the coin 1,000 times and got 800 heads, you're going to say I was cheating, because the probability of that happening is at least 800 is so small that you're going to say that's cheating. Do you see that? And that's kind of how all this works. All right, so here's a picture of the p-value. Okay, and by the way, this is real. So again, 4% at the time of people were getting COVID in the length of time at which they were doing the trials. And what they ended up having was only 1% of the people that got this. I think I'm trying to remember whether this was Pfizer or Moderna. Is one of those. It wasn't J&J, by the way, but it was one of those 2, and I forgot which one. They actually were really similar. And only 1% of those 40,000 people actually got it. So it turns out, if you take 40,000 times 0.04, that's bigger than 5 NP. And 40,000 times 0.96, that's NQ, also bigger than 5. And because of that, we can say the sampling distribution is approximately normal. Remember that from the central limit theorem? Very important, by the way. So now we can do a calculation using the normal distribution and say, what is the probability of being less than 0.04 if you have a sample size of 40,000 and a proportion of 0.04? And that probability turned out to be 0.004. Okay. And again, I did the research, I looked at the studies and all that. So trust me on this one. Sorry if I forgot whether it was Moderna or Pfizer. It was one of those, because it was a while that, I had to really focus on it. Okay. And by the way, I got vaccinated. I looked at this p-value. I did look at the p-value. And their p-value was small enough, and I trusted it. I knew they did it right. And since they had such a small p-value, that means that the World Health Organization and also I'm blanking the federal one, they accepted the vaccination. And hopefully you all know that happened, right? But they wouldn't have accepted it without the statistics. Wouldn't have happened. Because you don't want to give all of America a vaccination that doesn't work or maybe kills everyone. Right? So that's why you have to go through these trials. And by the way, the kills everyone, they didn't start with 40,000. Okay, and they didn't start with people. So they gave the vaccination to, I don't remember which kind of animal, it might have been mice. And you don't want a bunch of mice dying, but it's not quite as bad as people. So that's how it works in the real world. They start with a little small stuff like mice, and then they go with not too many people, and then they raise the number of people to get the p-value small enough. And then once the p-value is small enough, then they can actually say FDA, that's it. The FDA can approve it as an approved vaccination. Any questions on this? So since the p-value was less than the level of significance, which is 0.1, that means we can reject the null hypothesis. because we had too small a probability of this happening. So this 0.04 being the center or the mean, the proportion of the population can't be true for vaccinated people. So that means vaccinated people really do have a smaller chance of getting COVID. Okay, so let me tell you how you state it in statistical language. So this is very important. And that is, there is. So don't forget, the first two words is there is, with confidence intervals. What's the first word for confidence intervals? When you're interpreting the interval, not the, by the way, interpreting the interval is not the same thing as interpreting the level. When you're interpreting the interval, which is the important piece. Remember the word was one word. Starts with a W. For confidence intervals, very important. With. Remember that, with 95% confidence? So when you're doing hypothesis tests, there is statistically. Those three words are always there, by the way. And then the next word sometimes is there and sometimes it's different. So statistically significant evidence. So if the p-value is small enough to reject the null hypothesis, then you have significant evidence. Do you see? Do you know what the opposite of the word significant is? Hopefully you all do. It's an English word, not a math word. I don't know. Give you a minute or two. Because we're going to be using it a lot.
Is it insignificant?
Yep, insignificant. Well, that's a trick question, by the way. So if the p-value is big and you fail to reject the null hypothesis, then you would say there is statistically insignificant evidence. You'll also see another word besides this. Sometimes you'll see sufficient evidence instead of significant. But I tend to just always like to use the same word for you guys. That way you just get used to it. But sometimes you might see sufficient instead of significant. Okay, so there is statistically significant evidence to conclude that the population proportion of vaccinated people who get COVID is less than 0.04. Because that's what we wanted to show. That's the wordy way of saying that the alternative hypothesis is true. Okay, so do you notice that I wrote statistically significant evidence and I also wrote population in red? How come? You've seen this before many times in this class. So statistically significant evidence. I'm going to say it loud in case you're colorblind. Population. I'm going to say it loud because that's good enough too. Why did I say it loud? I'm not hearing y'all. Because if you don't put it in there, you're going to lose points on the exam. So get that in your notes. Okay, that's very important. Okay. So you need to learn how to use statistical language. And this is some of the statistical language. I want you to use that. Population, same idea as the confidence interval, is that the confidence interval was about the population, not about the sample. Do you remember that? And I noticed that some of you screwed up on the exam. And when I asked you to interpret the confidence interval, you use the word sample. I even have one say sample population. And those words should never be together. But again, it's very important that you know the keywords. Any questions at all on this very important example? Okay, and it's important to life. Do you see that? That's what I like about this class, is that there's no question that this is important, right, in the world. Hopefully you agree. Okay. By the way, I've watched this, and I study this stuff, and you can guess that I'm that kind of nerdy person. So every time they come up with a vaccination and a new, saying it's okay, I look at the p-value. And only once did they get it wrong. And that was when they approved the vaccination for 13, I think it was 13 to 17-year-olds, might have been 14 to 17. They did it too early, and they didn't have a low enough p-value, and they shouldn't have done it. I was like, what? It was close, but it wasn't quite there. And it turned out, fortunately, in the end, it worked, and that can happen. But the probability of it not working was too high for them they should not have approved it yet. They should have had a bigger sample size and waited a little bit longer. But all the rest of them were done really well. That's the good news. But that teenager one, for some reason, I don't know why they accepted it with a p-value that was bigger than they should have. But I don't get to choose. Okay. So just to note, this is important. The null hypothesis is what you are hoping to refute. The alternative hypothesis is what you're hoping to find evidence that it's true. And when I say hope, it doesn't mean it's good for society. It means you get to publish. Okay. Sometimes you're going to find something terrible is true. Right. And you're not happy that it's true. You're not happy that you're finding that this is killing all these people. Right. But what you're happy is that you found it so that now you can give warnings to help people not die of it. Do you see that? So now you can actually, say, hey, look at that. We can publish the fact that, for example, do you really want smoking to kill everyone? No. And when they did that test, their alternative hypothesis is that smoking kills people, right? So I wouldn't, that you shouldn't be happy that all of a sudden that people are just dying of cigarettes. But what you're happy is that you found out that cigarettes were a cause of death so that you can help people live longer. Do you see how that works? So just note what good and bad is. It's a weird kind of thinking. Any questions on this so far? Okay, now let me give you another one. This is a Tahoe one. I apologize if you're not from Tahoe, but I'm going to mention something that the most important statistics in Tahoe that's done. And if you've been to Tahoe, what's special about Tahoe that Mammoth doesn't have, for example? Neither does Modesto or or Vegas. Hopefully you all know Lake Tahoe. We have a beautiful lake. If you've never been to Lake Tahoe, please come to Lake Tahoe. It's one of the prettiest places in America. And one of the things that makes it so beautiful is we have one of the prettiest lakes in the world. And what makes it beautiful is that it's not, we don't have a lot of gross stuff in it. Does that make sense? So one of the things that you want the pH. And I'm sorry if you've never had chemistry, but you might have heard the word pH. So the question is, we want the pH to really be the pH of water. The pH of water is 7, by the way. So does the average pH in streams that flow into Lake Tahoe differ from 7.0? Because if it does differ, then we need to clean up those streams before they get into Lake Tahoe, or Lake Tahoe is going to get dirty and gross. But if those streams have a pH of 7, that's a positive. That means there's that's one item that we know that the stream water that's going into Tahoe is not going to hurt our lake. Do you see that? So very important stuff. And by the way, every year I am part of, and by the way, I'm not the organizer. I'm just a volunteer. And there is something called Snapshot Day. And what I get to do, and I've been doing this since the beginning, actually, it's been like 20 years or some, a lot of years, I don't remember how many, but I, along with a whole bunch of other volunteers, not statisticians, just a bunch of volunteers, we measure the pH and some other things in the streams that flow into Lake Tahoe. And we bring that in on that same day so that they have measurements every year to see if things are improving or not improving or getting worse or whatever. And this is one of the things we measure. And we do this with lots of streams, so we have a large sample size, and we can actually do statistics on it. And I have volunteered to help them in actually running the fancy statistics. You know, even though they have people that know statistics, but I'm the professor. So I've been helping them with this. So here is H naught and H1. So H naught colon. So far that's exactly the same as what we had before. But now the survey question is, what is the pH reading of the water that we just grabbed out of that creek? Does that make sense? And when you do a pH reading, you might have 7.4 or 6.9. Do you see that? So it's a number, not a yes, no. And that is mu. So mu, and then equals 7, because we want to find out if it differs from 7. H1 colon mu. So now this is very important. You need to look at keywords in the question. This is going to happen a lot for your assignments, for your discussion post answers, your exams, and your project, by the way. You're going to have to know and see that keyword differ in this case. Differ is not less than, not greater than. It's the symbol is not equal to. By the way, very hard to type a not equal to. But you can write not equal to in words if you can't figure out how to use the equation editor on the Canvas or my math and whatever it is. But just let you know that there is a way of making the not equal to happen. And by the way, I don't know if you realize I'm using Google Docs, and Google Docs have a way of doing not equal to also. So it's mu not equal to 7. This is called a two-tailed test, because by not equal to, that means it could be on the high side or the low side. The high side is the right tail, and the low side is the left tail. And if it's on either of those sides, then that means it's not equal to 7. Do you see that? Any questions on that? So this is called a two-tailed test. Okay. And the idea is, by the way, if you're not equal to 7 on either side, like if you're 9, that's really bad. If you don't know chemistry, I'm just going to tell you, then you have really acidic water. And acidic water is awful. It's going to kill the fish. It's going to be all kinds of bad things to whatever's in there. Okay. And by the way, you're not going to want to swim in it either. Okay. On the other hand, if it was, say, 4, much lower. I'm sorry, 9. Sorry, 9 would be basic, not acidic. Sorry if I said it wrong. 9 is basic. 4 would be acidic. And acid's bad, base is bad. Okay, for all kinds of stuff. You want it to be water. Okay. And by the way, you don't have to know chemistry for this class. If I even got it wrong, and I fixed it though. Okay. So a type 1 error. Remember, we're doing things in order. The first step was to write down H naught and H1. The second step is to decide what the type 1 and type 2 errors are and what the ramifications are. So that means you're going to reject the null hypothesis when the null hypothesis is true. That's just the definition. If you reject the null hypothesis, that means you're going to say that mu is not 7. That the water that's coming from the creeks into Lake Tahoe is not good water. It's either basic or acidic. And if you're going to say that, what's going to happen is you're going to have all these regulations put into place. You're going to spend millions of dollars to get that pH back. Do you see that? But null hypothesis is true. The pH really was 7. You totally wasted money. Do you see that? You spent all this money trying to make things better and they were already good. That's terrible, right? But let's look at a type 2 error. Type 2 error is you fail to reject the null hypothesis when the alternative hypothesis is true. Okay, in this case, no regulations occur because you're not able to, you're not going to say, hey, we have acidic or basic water. We're going to say, well, it might be okay. So we're not going to be able to get millions of dollars. No regulations are going to happen, but the flow into the lake is going to end up harming it severely. You're going to end up having all this acid or base water coming in, and Tahoe is going to get ugly. Any questions on that? And we're going to lose what we call lake clarity, kind of the blueness of Tahoe. Okay. Okay. Well, both are pretty bad, right? Depends who you talk to, right? Because remember, if you got to put millions in, that means we got to raise taxes. Okay. If we don't put the millions in and it was really bad, then lake loses beauty. So this is one of those where it might be a battle, might be a Democrat-Republican battle. And I'm going to go for the middle ground, even though it may not be true. If they're the same, we're going to say 0.05. Do you see that? Okay. But if type 1 is worse, so that would be if you're on the, kind of the, high environmentalism kind of thing, type 1 is worse, right? Then you're going to use 0.01. On the other hand, if you're more on the, we should never raise taxes and waste our money, then you're going to use alpha's 0.1. I never tell you what you should be politically, but I'm going to, mention what politics is, and this is politics. Do you see how that works? It's like a mix of science and politics. Okay, what really makes you pissed is when the politicians don't understand statistics. Hopefully you understand why I don't like that. And that happens a lot on both sides, by the way. So I'm not going to get into that too much. Okay, so let's suppose that X bar, that was a sample mean. Remember, all these people are doing this testing. I was one of them. But there were like 100 of us all testing different creeks. I test usually 1 or 2 creeks is what I do on snapshot day. Okay. I live walking distance from one, so sometimes I'll do that one. Okay. And let's say the p-value was 0.27. So 0.27 is greater than 0.1. No matter which of these you chose, by the way, 0.27 is big for the p-value. Do you see that? So here's a picture with a two-tail test. Then you'll actually see the two tails. The X bar was 6.4. So by the way, the other side of that, 6.4 is 0.6 away from 7. Do you see that? So if you want to show the other tail, you're going to have to go 0.6 above 7. And that'll be 7.6. So the p-value is the probability of either being less than 6.4 or greater than 7.6. So 7.6, a lot of people have trouble finding it. Any questions on how I found the 7.6, even though X bar was 6.4? It's the symmetry in the picture. Any questions on that? Okay. And the p-value, the area of these combined two tails, was 0.27. Because of that, there is insufficient evidence to make a conclusion that the population mean pH for all streams into Lake Tahoe is not 7. This is a very fancy way of saying we don't know anything. Okay, but I do require you to say it in a fancy way. Don't just say we don't know anything. You need to be able to say insufficient evidence. Do you see? You need to say population mean. Those are keywords, as I showed you before, same keywords. Last time it was proportion, now it's mean. Don't get them confused. This is mean because you take a pH reading and it's a number, not a yes, no. Any questions? And to be honest, it's really hard to read that number. If anyone tried to read a pH little thing, you have to like look at the color and decide what the color number is. It's so hard, but you don't have to worry about it in this class. But in the real world, you sometimes do. Okay. Just a note, by the way, at this point, once we've made this conclusion, do you have to worry about a type 1 error or do you have to worry about a type 2 error? Any thoughts? Okay, once we've made this conclusion, we found insufficient evidence. We failed to reject. Remember, a type 2 error is when you fail to reject, but the alternative hypothesis really was true. That's a type 2 error. Well, that could happen because we failed to reject. You see that? On the other hand, a type 1 error is when you rejected, but the null hypothesis was true. That didn't happen. We didn't reject. So at this point, a type 1 error is impossible. So after you've done the study, only one of those will be possible, the other one won't. Any questions on that? And I want to mention another thing. 0.27, is that a lot bigger than our 0.1? That's pretty much bigger. Do you see that? It's not that close. If it's not that close, you usually just give up. It's kind of hopeless. On the other hand, if let's say we got, instead of 0.27, let's say we got 0.13. That's real close to 0.1, but we had a low p-value, but not quite low enough. And then you're going, crap. My guess is that I just didn't have a big enough sample size. So in the real world, you go and spend the money and get a bigger sample size. And then hope that you get a low p-value. Sometimes it just means you're going to get a high p-value. You still don't know for sure, but at least you have hope. If the p-value is really big, your hope is gone. Do you see that? Okay. One kind of an analogy I like to do is soccer. Okay. So let's suppose that you're playing soccer and there is 1 minute left in the game. And you're behind 12-2. And your player is about to kick the ball and you think they're going to make the goal, but the other team smacks the player and the referee doesn't quite notice it. Are you going to yell and scream at the referee? What do you think? Foul's not called. Any thoughts? Okay, the answer is no. You're down 12-2. You're not going to win this game. Do you agree? That's kind of like when you have a p-value of like, say, 0.9. There's no reason to do a bigger sample size. That's like going to the referee and complaining. Do you see that? Saying, hey, you need to watch the video and see it. Because, hey, yeah, sure, there was a foul, but you can get 1 point. Now it's 12-4. And now there's 30 seconds left of the game. You're not going to win. There's no chance. Do you see that? On the other hand, instead of 12-3, if the game was 7-6, you're losing. And the same thing happened. Oh, yeah, you're going to say, hey, referee, you need to look at the video. Do you see that? Because you're hopeful that the referee is going to say, yeah, there was a foul. Doesn't mean you're still going to win the game, but at least you got a shot at it. Do you see that? Because you were close. Okay, now what if instead it was the opposite? What if you were winning 7-6 and this happened? And it was the last minute of the game, the clock is just about over, but the ref doesn't call the foul. Are you going to scream and yell at the ref? Okay, even you're close, but you're winning now. There's no reason to yell at the ref because you won. Do you see that? So if the p-value is, say, 0.09, and you're using a level of significance of 0.1, there's no reason to get a bigger sample size because you won. Do you see that? And you were able to reject the null hypothesis. Okay. In the real world, someone else who doesn't believe you might say, we need a bigger sample size, but you won't. Do you see that? Okay. And similarly, I mean, if you're ahead 12 to 2, you definitely don't. So if the p-value say 0.0001 or something, you would never complain. Do you see? You never say we need another study. So I want to mention that it's going to happen in your project. You have to analyze and decide whether you're going to need another study or not. And you can always rewatch this video, by the way. Any questions on that idea? Okay, so just a note, what does it mean to have a p-value of 0.27? And here's what it means. Okay, what it means is that you're saying that you have assumed the 7 right here as the mean. Okay, so if the population mean pH of streams in the Lake Tahoe is 7, and if we did another study of 45, of sample 45, sample size 45 samples, okay, there would be a 27% chance, 0.27 is 27%, that the sample mean pH for this new study would either be less than 6.4, so now if we look at the picture, less than 6.4 or greater than 7.6. Any questions on that? Okay, you're going to have to practice this a lot before you get good at it, just a warning. Okay, notice this is about the sample mean, not about population mean. Because it's the probability of a sample having that, not the population having that. Okay, if we want to interpret the level of significance of 10%, the nice thing is, right, I gotta move the chat box, sorry. What I just highlighted, do you see that? And this, do you see any difference? It's exactly the same. So by the way, if you're doing this, you can copy and paste that part. It's exactly the same, but then things change. So if the population mean pH of streams in Lake Tahoe is 7, and if we did another study of 45 samples, then there'd be a 10% chance that the new study would falsely lead us to conclude the population mean pH of water flowing into Lake Tahoe differs from 7. So this is another way of saying this is the probability of a type 1 error, given that the population mean is 7. So that's why it's a probability of a type 1 error. Any questions at all on these interpretations? They're not that easy yet. Okay, so let's do another example. And let me show you how you do this. Suppose you want to see if women are not drinking the recommended 2.7 liters per day on average. That's what's recommended, by the way, for women. Okay. So the first thing is H naught and H1. So H naught, mu equals 2.7. They are drinking to 2.7. Do you see that? Okay. By the way, the problem is not drinking enough. Drinking more water. Have you ever heard a doctor saying you're drinking too much water? Never, right? So really the issue is less water is bad, right? Not drinking enough. So mu is less than 2.7. So I'm kind of thinking this medically. Okay. Let's suppose we decided on a 0.01 level of significance. I only have so much time. So let's suppose that we collected data. I made this up, but you can imagine someone collecting data. And this is the data of the amount of liters per day that those women drank that you surveyed or observed or whatever. Does that make sense? And copy this. Let me show you. Let's go to the calculator. What do you think we're going to be doing? Which one? Calculator number.
15.
Yep. It's a hypothesis test for a mean, because remember that The survey question is, how much water did you drink today? And we had data, we didn't have statistics. So I can click on that population mean with data. And then I copied, I'm going to paste in the data. That was the data we had. Do we know sigma? We don't, you usually won't. So leave that blank. But what we do have to think about, is it less than, is it greater than, is it not equal to? And the idea is we've already written the null hypothesis and the alternative hypothesis, and the alternative hypothesis had a less than. So that means we need to click on and make sure it's clicked on less than. This mu naught, that's the mu in the H naught. So the mu in the H naught was 2.7. Do you see that? So I'm going to go 2.7. Any questions on that so far? And then guess what I hit? Calculate. And it gives me all the stuff I want. X bar was the sample mean, 2.54. S was the sample standard deviation, 0.4888. T. You've seen T before. When did we see T? Remember?
That T student thing.
Yeah, same thing. Turns out it's the same because we don't know the standard deviation, which you usually won't, of the whole population. Okay, in the real world, you never will, by the way. We have to use that student's T distribution, which is a like slightly variation from the normal distribution. And that T value is negative 1.9. Do you see that? And P is our P value, which is about 0.03. Any questions on that? By the way, on your assignments, you'll usually have to do more decimals, so it can't hurt to do extras. But I'm just going to show you 0.03. And that's what I got. P-value is 0.03. Do you see how I got it? So here's the conclusion. 0.03, notice, by the way, is greater than 0.01, right? If the p-value is greater than the level of significance, then there is statistically insignificant evidence. So there is statistically insignificant evidence to conclude that the population mean amount of fluid women drink is less than 2.7 ounces. Any questions on this example? Okay. Just a note, I'm going to say it, but I'm not going to like write it down. If you want to interpret the p-value, you'd say that if the population mean amount of water women drink really is 2.7, and if you surveyed another, I don't remember how many it was, how many number of those people, it might be 20, 35 or something. I have no idea, but you can count it. Women, then there would be a 3% chance that we have a less than, okay, that, and we'll go back here. The sample mean for the new study that you would do would be less than 2.54. Do you see that? Because that's what we got for our sample mean. That was the interpretation of the p-value. Level of significance is very similar. To start, not similar, exactly the same to start, is that if it is true that the population mean number of liters women drink is 2.7, and if we surveyed another, however many this is, women, then there would be a 10% chance, because our level of significance, a 1% chance, that was our level of significance, there would be a 1% chance that we would end up falsely concluding that the population mean ounces amount of water that women drink is less than 2.7 liters. So I know I said it fast and I didn't write it, but we can only do so much. I do have some templates. And again, you can always watch this, rewatch this on YouTube if you want. But here's a template. There is statistically significant evidence to support the claim that the population is either going to be mean or proportion. XXX. That's going to be relevant to the survey. Some of you by the way, some of you did not do the relevance to the study for the confidence interval question on the exam. And I did take off points. Don't just write down XXXXX, or don't just write down some general thing that doesn't talk about liters of water for that example. Does that make sense? Make sure that you are relevant to the study. And the template for when you fail to reject is exactly the same, except for an in instead of an insignificant. Any questions on that? P-value template, if, and then I write the null hypothesis is true. Don't write the null hypothesis is true. Write whatever that means. In our case, the population mean amount of water that women drink is, what was it? Something 2.7, was it? Yeah, 2.7 liters. And if another sample of however many women we looked at was taken, don't use XXX, please. Then there would be a XXX probability. That's the p-value. Don't write XXX, please. That, and then the results of the new study would be at least extreme as results of the study, but don't, if it's in parentheses, don't just write that. Make sure it's in, talking about women drinking water in this case. I'm a man, I'm drinking water, but hopefully it's okay. Interpret the level of significance. I also have a template for that. It starts exactly the same, up to the word A. And then XXX probability, that'll be the level of significance probability. Okay. And you can say percent chance, if you feel like it, that the new study would result in falsely concluding that whatever the alternative hypothesis is true. Okay, but don't just copy and paste this without changing it. You need to write about what the question is asking. I will take off points if you just copy and paste. Okay, understand it. That's most important. Any questions on this? Okay. So let's take a look at this one right here. Do the majority of people want to eat instead of drive while in a car? Run a full hypothesis test. So this was an article, and I'm going to show you the article and how to get there, about self-driving cars. Because you think about, why do you want a self-driving car instead of a car you have to drive? Well, one is so you could have lunch. Do you see that? Right? And there's a lot of things they asked we'll look at it, but we're only going to look at this one. We're going to look at so much. Maybe you want to drink alcohol. Okay. Well, hey, if you're in a self-driving car and it truly drives itself, you can be as drunk as you want. Do you see that? In 50 years, DUI people won't even know what that stands for, by the way. So they ask people about what they want to do. Is it something you care about? So let's go to, so first thing is that here was the article, and this was the title of it. The link won't work. Do not post the link of an article that you find on our library. So this is the LTCC's website. If you go to library, and we go to find articles, we go to academic search complete. Okay. The first thing you have to do after that is you have to log in. It's the same username and password that you log in for Canvas. That's the good news. So hopefully you know your Canvas login username. If not using the computer, it'll probably just do it for you like it did it for me. But it's that username and password. And then it goes to here. I'm going to copy and paste that title. Okay. You can also do specialized searches, peer-reviewed, makes it a journal article so that it's actually trustworthy. Because you're going to have to do that for this discussion post, by the way. You're going to search. And there's the article. Okay. Notice this is academic journal. That means it's trustworthy. It means it's peer reviewed. And I click on it. And here's the article. Are autonomous vehicles only a technological step? The sustainable deployment of self-driving cars on public roads. I'm not going to read this whole thing because it'll take all day long. But we can look at this. And if you want to look at EAT, it's here, but it was somewhere else too where I found it. That was more interesting. Thought it was somewhere else. Sorry if I'm not. Oh, no, maybe that was it. Ah, there it is. Eat a meal or snack. That's what I want to look at. And 51% said that, yeah, self-driving cars would be great because I can like eat a meal or snack while I'm driving. Do you see that? While I'm in the car by myself. Okay. So 51% is what they got. And I'm just going to, you can trust me, the sample size they had was 4,700. It was a big sample. P hat, remember that little hat? That's the sample proportion is 0.51. Do you see that? Okay, so because of that, we can now go and work it out. So I'm going to go to my calculator and go back to the calculator menu. And what calculator number? This isn't supposed to be a hard question. It's supposed to be there. Yeah, it's 16 because we're doing a hypothesis test. And it's a proportion because it's a yes/no question. Hey, is it important to you to be able to eat a snack and stuff? When, is that an important piece of having a self-driving car? Do you see that? And the person saying yes or no. So a hypothesis test for a proportion. Not to mention that we have a p hat. So in this case, it's asking different things because it's proportions. We had n, and n again was 4,700. We had x. X, we're going to do a little work on because p hat was 0.51, n was 4,700, so we need to multiply. But we can do that easily. I'm going to go to scientific calculator and 0.51 times 4,700. And you get 2397. And that's an X. Any questions on that? P naught. So P naught is what we're hypothesizing. In this case, we want to find out about majority. That was 0.5. Do you see that? Because being the majority means greater than 0.5. So P naught is 0.5. And we want to be the majority. That was a greater than. And hit calculate. Okay, now it's Z, by the way, not T. We're not talking about means, we're talking about proportions. Z is 1.37, 113, etc. And the p-value, and by the way, this Z is called the test statistic. That's what this thing is. So if you're asked for the test statistic, that's what you're going to say. Z equals 1.3711 or something. The p-value is about 0.09 or so. Okay, and if the p-value is 0.09, this is, let's say, greater than 0.05. This is kind of standard. Let's pretend we did standard. So that means you fail to reject the null hypothesis. And again, run out of time, so I'm going to say it. That means there is statistically insignificant evidence to conclude that the population mean, population proportion of people who want to eat and have a snack while being in a car when they're by themselves is greater than 0.5, or a majority is a way of saying it another way. Any questions on that? Okay. Let's do one quick example before I start doing the next thing. Normal body temperature is 98.6. Is the average different for marathon runners? Okay, do you think it is? We'll find out. Actually, we won't really find out because I made up these numbers, but but you could do a study like this. The 38 marathon runners whose temperature was measured had a mean body temperature of 9.4 and a standard deviation of 0.7. What can be concluded at the 0.01 level of significance? Any questions so far? Okay, I'm going to say what we're doing instead of write it out because it will take too long to write it out. But H naught will be that mu. It's mu because you're going to ask what was your temperature. Do you see? Mu equals 98.6. H1 will be mu is not equal to 98.6 because of the keyword different. So now we can go to our calculator. Let's go back. And what calculator number do we want? So it's population mean, it's mu. And we don't have data, we have statistics this time. So this is going to be number 14. And it's going to ask us for a bunch of things. Do we know sigma? Do we not know sigma? We don't. So sigma unknown. S. By the way, if you hit sigma known, the S becomes a sigma. But we don't know sigma, we only know S. And S was 0.7. X bar, that was 98.4. N, that's our sample size. That was 38. And then mu naught, that was the hypothesized mean, which was 98.6. And then we had a not equal to, if you remember, because it's different. And I hit calculate. And if we're going to be using a level of significance of 0.01, we got a p-value. We got a test statistic of negative 1.76, p-value of 0.0864, etc. 646, for example. That p-value is bigger than 0.01. So we fail to reject the null hypothesis, and there is statistically insignificant evidence to conclude that the population mean temperature for marathon runners differs from 98.6. Any questions on that? Okay, what I want to mention next is the secret word. So the secret word is population, because if you don't refer to the population when you need the population to happen, okay, or by the way, if you don't refer to the sample when you need the sample to happen, I'm going to take off points. So population is a secret word. All right, I want to spend the next few minutes, not too long. Next week we'll spend longer, by the way, talking about project 2. So the first thing is, and I think I mentioned this last week also, is that you are allowed, if you want to keep your partners for project 2, but you don't have to. So if you didn't like your partner, didn't get along or whatever, then let your partner know. That's kind of important. Don't be mean that you're changing partners, and that's okay. You're allowed to do that. If you want to leave your partner and find new partners, then what you should do, if you go to discussions, you can go to Project 2 discussion forum. It's different than Project 1. Don't go to the Project 1 discussion forum, please. And post something, I'm looking for a partner or whatever. Does that, or if there's only 2 of you and you want a third, which you should, if there's only 2 of you, then ask to see it. Anyone want to be a partner with me? We have 2 of us. Is that clear? So that's the first piece for Project 2. There will be 2 main components of Project 2. Any guest here think last week and this week? What do you think the key main components of Project 2 will be?
Hypothesis testing.
That's one of them.
And
What was last week all about?
central limit theorem.
No, that was the week before.
No.
Confidence intervals.
Okay.
Yeah, that was pretty recent.
Yeah.
Yeah, confidence intervals. So it's really all about confidence intervals and hypothesis testing. Okay. The standard error will be a big piece too. We'll get into. I will let you know you're not quite ready yet because it's a chapter 10 project. So chapter 10, you're going to be doing a confidence interval hypothesis test for a difference between means. So I'll let you know that. I also want to let you know this is not Project 1. The focus will be on confidence intervals and hypothesis tests. It will not be on your sampling technique. And any guess on what you're allowed to use, what you're required to use for a sampling technique? Anything you want. So convenience sampling is allowed. You have to admit to it. That's all. You have to admit to it because that's not the focus of this project. In the real world, convenience sampling is not good. But again, I don't want you to spend all your time doing that kind of stuff. Does that make sense? I want you to spend all your time on the confidence interval and hypothesis test. So kind of the general idea of what we did today and the general idea of what we did last week, we're going to put that together with differences next week. And that'll be what's going on. So that's why we're not spending a lot of time on this project today. Next week, we'll spend a lot of time talking and I'll show you all the stuff. We're not quite ready yet. But let you know, at least partners, you should be thinking about that. And it's a very different project. It's not Project 1. It will be 2 variables instead of 1. So it's not even this week's. Okay, but we'll do that next time. So anyway, that's pretty much everything I had to say for new stuff. And I always like to end at around 40 after, and it's 39. So probably it'll take a minute for me to find the stop button. See if I can find it. There we go. I'm going to stop the recording.